Hey everyone, welcome to the stream. So let's review what we did yesterday. We wrote an assembler to translate assembly language program into hack machine code. So in the assembler we wrote, we handled white space and instructions, but still we haven't wrote the code for handling the symbols. So before we continue building this program, let's review what exactly we did. So this is the hack assembler, hackassembler.py. hackassembler.py, and let's see, we can add an assembly program using the command line. So if I give it hack.asm, so now if I check the add directory, I will have add.hack program. So this is the translated program that we get after we run the tool. Let me find the pseudo code. So this is the pseudo code. So we created this method or this function reading and passing commands. So we created a parser class just for that. After that, we also created a class to translate mnemonic to code, which is this one, class code. Now after that, yeah, that is it, basically passing and translating. But now we need to create a symbol table. So to create a class symbol table, not class exactly, we'll see what to name it, but see, the basic idea is to create a table like this: loop, sum, and the addresses. So just like I said earlier, that we are only handling the commands, which is basically inside the which is basically a white space and this kind of blank lines. And after that, we are also handling the instruction, which comes into two types of categories, either A type and C type. But we are not yet handling the symbols which comes into, let me open up this slide for that. Handling predefined symbol, handling symbol. So yeah, this is the third thing that which we have to handle: symbols. Now symbols comes into three types of categories: one, predefined symbols, label symbols, and variable symbols. So the kind of predefined symbols we have are R0, R1, R2, screen, KBT. So we have used this symbols, but we are yet to use this same symbol, but still we will have to take care of them inside this assembler. So it will be simple to take care of this predefined symbols, because we are basically given all the values that we have to map to these symbols. So that is it for predefined symbols, and these predefined symbols can be used with A type instructions only. So like this one at R1. So this R1 is a predefined symbol, and our assembler has to translate this R1 back to R1 translates to 1 as a predefined symbol. So we have to translate this at R1 to at 1, and after that we have to place this 1 as the value of this A type instruction. Now we also have label symbols. So label symbols starts with left rounded brackets and end with right rounded brackets. So this is what a label symbol looks like. And in this sample program we have 3 label symbols: loop, stop, and end. And inside this symbolic table, what we have to do basically is, whenever we encounter a label symbol, this label symbol has to map to a number which is a line number, and this line number is the one which comes after, just immediately after this label symbol. Now here's the thing, we can have a comment just after this label symbol. So I'm not yet sure if we should give the line number of that comment, because it doesn't matter actually, because it's not going to run anyway. So we can give the number which is immediate, line number of the instruction which is immediately after this label symbol. So we will have to create a logic where we can find these numbers which are immediately after this label symbols, and we have to write inside the symbolic table. And this label symbols, we are storing the line numbers, because we will have to use so we are storing this line numbers because we are using those line numbers to jump to that instruction. So just like here we are using at loop. This at loop is basically go to the loop, which means go to the line immediately after where this loop label appears. So go to this 4th line. So therefore we have to first map this loop to the line number, so that whenever we encounter this kind of instruction at loop, we know where we want to end up, which is the line number represented by that specific label symbol. So that is it for the label symbols. And after that we have variable symbols. So anything which is not a label symbol, which comes in this kind of at instruction, is a variable symbol. So inside this sample program we have at I as well as at stop. So this at stop, at loop, and at end are label symbols, but after we pass this label symbol, so how can we distinguish between label symbols and variables? So this label symbols have the corresponding label. So this label corresponding declaration of the label symbol. So for this at loop we have at loop declaration. But whenever we come across any symbol which doesn't have the specific declaration of this label symbol, that means it's a variable symbol. So this at I is a variable, like at sum, at I. So we have two variables inside this function. Now for this specific heck assembly language, this variables maps to a particular value, and this value will be starting from 16. So this 16 is basically a memory address, and it will start from 16 and so on. So the first variable will start from 16, the second 17, and so on. So we'll have to develop a logic of this kind. Okay, that is it for the symbol. And yeah, we have to develop this kind of data structure where we can store the symbols and values of that symbol. So let's see how we can create such a function. I think we should create a class for symbol table, I guess. What should it contain? First of all, we will create that particular class, will create an empty symbol table. So in our case, we will be using dictionaries, Python dictionaries, to store the symbols. So the key will be that symbol, and value will be the value of that particular symbol. Okay, so inside that class we will create an empty dictionary for symbolic table, and after that we have to assign the predefined symbols. So these are the predefined symbols, R0 to R15, and these are the symbols. And after that we'll scan the entire program, which basically means we will open up the file of that program and read line by line. And for whenever we encounter an instruction, so this first pass is for just for this label variables. So in the initializing stage we have the predefined symbols inside the symbolic table. So after that we'll take care of this label symbols. So to take care of this label symbols, what we will do is we will read line by line. We won't be executing this instruction, but we'll just read line by line, and whenever we encounter this label symbol, which looks like this one, we will store this. We'll check the symbolic table and see if that label is inside this table or not. If it doesn't, then we will store that label, and after that we also need to pass the line number of the next instruction. So we'll also have to record the line numbers as we read the lines from that program. So when we reach the end of line, that is it for the first pass. And after the first pass we will have the label symbols inside our symbolic table, and after that we will start the second pass, which is just a fancy name for reading the file. For this loop, we will first create a variable name n, and it will run from 0 to 16. Sorry, it will start from 16. Why 16? Because as I said earlier, the variables start from the 16 address. So it will start from 16, and whenever we encounter a variable whenever we encounter an instruction which looks like at and I, and we will check the symbolic table if that particular variable exists inside symbolic table or not. If it doesn't, then we will assign the n value. The n value will be 16 for the first variable, and after that, and so on. And at this stage we'll also, I think we'll also translate the code as well. So instead of explaining it, let me just start writing the code. So first we'll create a class, we'll call it symbol table. Okay, so after we have symbol table, what we need to do is create a dictionary for the symbolic table. So let's call this dictionary, what should we call it? Symbols. Yeah, it's all right. Let's just create an empty dictionary for now. Now after that, we also need to create a function. We'll create a function to store the predefined symbols. So predefined, what should we call it? Save, store. Let's refer add. Yeah, add. Let's call it add pre-def. Yeah, pre-def. And inside this function we'll store this values from R0 to R15, and this green up to this, and that will be the last predefined symbol. So first of all, for R0 to R1, I think I should write a loop for R0 to R1. So let's see, for I in range will be for 15, 16. So this will run from 0 to 15, and I want to store self dot symbols can I store it like this? R plus I will start from 0 up to 15. So this will be the key, and for value we'll store I. So this will give us R0 to R15. Let's test this program. Let's see what we want to do. We are opening this file for writing, opening this file for reading, which is the assembly program. After that, for each instruction we are passing it. So do we need to pass it right now? Well, let me comment this code out. We don't need to open this file first. So in the main program, let's first get this symbol table. symbol table. You don't need to pass anything. After getting the symbol table, wait, first I need to call this add predef inside the initialization. So after, when we create this object, we will get symbols, predefined symbols. So let's check if we are getting those symbols or not. So we'll print st dot symbols. Symbol. I think I might have to use a loop. Let's see if this works or not. Yeah, it didn't work. String to int can only concatenate string, not int to string. Okay, I get it. So I have to convert this I to string. Do we have str? Yeah, so inside the dictionary now we have R0 up to R15 and the values are 0 to 15. So it is working. So after that, after we have the R0 to R15, which are the registers, we will need screen, keyboard up to that. So we'll have to manually enter all of those. So to do that, I'll write self dot symbol and screen. Wait, this should be capital. Screen, and the value will be 16,384. Okay, let me copy this. KBD, SP, LCL, arg, this and that. Now we have KBD. This will be SP. Oops. SP. After that we need LCL. LCL. ARG. ARG. This, that. Okay, let's change the values as well. For KBD we have 24,576. SP will be 0. This should be 1, 2, 3. Okay, wait, I think I missed one. We have SP, LCL, R. This, no, I didn't. That's all right. Okay, now we have all of the predefined symbol. Let's check the program again. So now we have all the predefined symbols inside the symbolic table. Now we need to create a logic for the first pass. So for the scanning of the program, we already have the logic. So what do we need to take care of? We need to take care of checking for this label symbols and assigning the value in the dictionary. So let's see how we can do that. So while we are running this first pass, we need to check for this kind of instruction, starting with a left rounded bracket. So we need to check if this instruction is like this one, and if it is like this one, we need to add the line number. Okay, so should I write a different function for this pass? I can write this first pass method inside symbol table as well, because we're basically adding the symbols anyway. So let me try to do that. If I write definition fine, I will call it first pass. First pass, and do I need to pass anything? Let's see. I can pass this argument ASM so that I can loop through it. So yeah, I will pass the file. I'll call it file, or better I should call it program. So after that, what I will do is I will loop through each line in that program for instruction in prog, and for each instruction I will check if it is of type label. So for that, what I need to do is, let's see, should I use a regular expression? No, I can directly use if instruction dot 0, which will be this one. But before that, I will have to trim the instruction. So to do that, I will write instruction is equal to instruction dot strip. This will strip all the white space around from the left side and the right side. So after we do this, now we can check if instruction 0 is equal to if instruction 0 is equal to left rounded bracket, that means we know that this instruction is of type this one. Now before we do that, we also need to track the line numbers. So for instruction in program, let me define a variable. We'll call it line number. It will be 0 initially. Wait, let me save it as -1 initially. It's because we are starting the lines from the 0th index. This will be the 0th line. We are going to ignore the comments. You can use this parser function as well. Parser function has this method check type, which will check if the instruction is of type A or C, or it is just a blank line. Yeah, so we should use this parser function. And if we use the parser function, we don't even need to strip the instruction. So let's use the parser function. P is equal to parser, not function, class, parser inst. So this will give us a parser object. Now we can call this check type method. Before we can call it. So this parser function will first of all clean up the instruction. So when it cleans up the instruction, it first strips the instruction, and if it is a comment type instruction, basically if it is a comment, then what it will do is so this will check for the comment. So if it is comment, the C index will return the index. So if it is C index is 0, that means it is this kind of comment. So it will replace the instruction with just nothing. And if it returns -1, that means it is not a comment, and in that case it will just strip the instruction and it will store it inside the instruction. So it will be the case for this kind of instruction, A type or C type. And if it is neither 0 nor -1, that means we have this kind of instruction, which is an inline instruction, inline command. And in that case it will strip this command and store just this instruction. Okay, so inside instruction we will either have this instruction, but now we need to take care of this type of this type of instruction as well, because previously we were not taking care of the symbol. So I will have to change my parser function, because we now have this kind of symbols as well. So for that, what we can do, so we don't need to clean it up. Yeah, it works. So this class as it is now, it will also take care of this class, this type of function. So during the cleanup step, this will be just a regular instruction. So let's see, this check will return 0, -1, it will return -1. So we're just stripping the instruction. Cool. So we will have the instruction. So let's see now. So after we pass it, now we don't need to strip the instruction, because we already have the stripped version inside the parser object. But we need to change this check type method. So if the instruction is empty, we just return. So it will be just type, it will be none. But if it starts with @ it will be A type. If it starts with nothing, so now I need to change this. If that self dot instruction starts, wait, instead of doing that, I can write another elif, and this will be for if it starts with a left rounded bracket, then the instruction will be of type, let's see, what should I call it, just L for label. So now for this step, what I can do, p dot type equal to L, which is label. So if the instruction is of type label, what do I need to do? First I need to increment the line number. Wait, no. Before I do that, I have to write this logic. P type is equal to either of type A or P dot type equals to C. That means if it is either of type C or type A instruction, in that case only I need to increment this by 1 line number. So because we are ignoring the comments and the blank spaces, so if it is this type, then only we are incrementing the line numbers. But when we encounter this kind of instruction, which is a label, what we need to do, let's see. In that case also we are going to increment the in that case we will going to increment the line by 2, because so this is how it will work. When we run the post pass, this will be ignored, so line number will remain -1 or this comment. But when it comes to this instruction, it will go inside this if statement, because it is of type A and the line number will be incremented, so line number will be 0 in this case. For this case it will be 1, for this case 2, 3, and this will be ignored, this blank space will be ignored. And when we come to this line, so it was 0, 1, 2 and 3, and when we come to this line, line number is yet still 3, but we don't want to increment it to 4, because 4th is this line, which is basically a pseudo instruction. Pseudo as in we don't need to pass the binary instruction of this instruction. So this will be the line number of this instruction will be ignored. So after that the line number will be 3 plus 2, 3 plus 2, which will be 3, 4 and 5, 3, 4 and 5. So after that the line number will be 5. And now what we need to do is check if this variable is inside the symbolic table or not. So for that I have to write another method inside the symbol table. It will be check exist, let's call it exist, and I will pass the symbol. So this will check if the symbol exists. Okay, do we have a method for that? Access dictionary methods. Keys, return a list containing the dictionary. Update values. Yeah, I think I can use get. So what will this get return? A value to return if the specify key. Yeah, so I can use get. So to do that, symbols dot get, and I will pass the symbol. So check if that key exists or not, and I also need to, yeah, by default it will return none. If it equals to none, that means the symbol doesn't exist. In this case, what do we need to do? We add the symbol and value. So we also need to pass the value, separate symbol that equal to value. Wait, no, shouldn't write this logic inside this function. This function is just for checking if it exists or not. So instead of writing this, I can just return false in this case. Else return true. Right, so we have a exist function. I can call this function over here, self dot exist. Wait, before I do that, let me after removing it, I will check if the key exists or not. But to do that, I just need to pass this symbol. So I will have to parse this symbol. Let me show you what I mean. I just need to get this symbol from this instruction. So I will have to extract just this part and remove the brackets. So how can I do that? Let me see if we have a method like that. I can do just this p dot instruction and slice it starting from 1 up to -1. So this will give us just that. So let me check if it works or not. So suppose this is the instruction, and if I pass 1 to -1, it should return h up to this exclamation point. So yeah, we are getting it. So this is correct, and we are passing it to self.exist, and this will either return true or false. So if this returns true, no, we should check for the negation. So if this returns false, that means it is not inside the table, and in that case we need to store the symbol and the value inside the table. Now let me write a method for storing the value. So we'll call it add symbol. Yeah, add symbol will be fine, and I will pass the symbol and value to this method. This method will simply add the symbol and value. So I can do symbol self dot symbols, and I can pass the symbol as the key and the value as the value. That's it. So if self dot not exist false, I should get this. Symbol, let's call it symbol. Now I can call this function add self add sim, and I will pass the symbol, and as the value I will pass the line number. So in this case line number will be 0, 1, 2, 3 and 4. Line number. Cool. So what else do we need to do? Let's see. Just need to add, and yeah, this is basically it for the first pass. So let's see if this function works or not. We'll have to call this first pass function. So for that I will have to uncomment this. For instruction, now I can call st dot first pass and pass the ASM, which is the assembly file, and this will do the first pass. And after it is done with the first pass, let's also print the state of the symbols. Okay, let's check if this works or not now. Oops, I forgot a colon. Is this an invalid syntax? Why can't I use a negation operator? Wait, let me check the docs. We do have that operator, right? Comparison. Yeah, don't have this operator. We have not. What the heck happened? So it was complaining about this symbol. Should be not. Okay, so before the first pass and after the first pass, wait, nothing is happening. No values were added. Wait, okay, I see. Because add.assembly doesn't contain any symbols. Let me check add.asm. Yeah, it doesn't have any symbols. So I will have to pass a program which does contain symbols. So this max function contains symbols. So I will pass max max.es. L is for the leaving out the symbols. Wait, in this case as well, nothing happened. Let me check this function as well. Yeah, we do have symbols. So why did it not work? Let's check. So what am I doing is I'm opening the file and I'm passing it to st.firstPass. First pass program. Line number will be -1. Let me check even if it is working or not anyway. So let me print the instructions. I just need to check if it is even calling the function or not. So yeah, it is calling. Wait, but why is there space and this? Yeah, the spaces for the commands. And for output dot first. So it is calling the function. Okay. Is it even checking the types? P dot type is equal to A or P dot type is equal to C. It will just increment the line number. And in this case, it will check if it is L. So let's see if am I even changing the type. Okay, I see now. Right, no. I'm passing it to P dot parser, right? So it will first initialize the instruction, and after that it will call cleanup and check type. So in cleanup, it will just assign it back to instruction after stripping the white space. I don't touch anything else. And use the check type, it will come to this condition. If self.instruction starts with left opening parenthesis, then it will change the type to L. We have L, right? We have type. So this should return true. P dot type is equal to L. Let's see if it is even returning the P dot type correctly or not. Print P dot type. So for this, we are getting the L. So that means the condition is working, and we are going inside this condition, and we are incrementing the line number, and we are getting the instruction. So I think it might not be executing this function head.symbol. So that means self.exist is not returning something correctly. So let's check it again. Instead of printing this time I will print let me print symbol this time. Yeah, I am parsing the symbol. I'm passing the symbol and I'm passing it to self.exist, and it will check if this self.symbol.get symbol, if it is none, then return false, and if it is, so it will return none when the symbol is not inside the table. So this will return false. So this will be false and not false, so it should be true. So let's check if this condition is working or not. Okay, it means the condition is not working. It's not printing the symbol. That means we are not getting inside this condition. Why is that the case? So that means this get is not working. I need to check if this returns something or not. Oops, not here. Okay, let's print it. Where is it printing? None, none, none. So for this case it is printing none, for this none, for this none. Okay, so it is printing run. And if it equal, okay, wait, I see now. It's not a string, so this should work now. Awesome. So now we are getting these symbols, and let me check if they are correct. So for this function we have loop, stop and end. Right, for this we have output first, output D, and infinite loop. And for this program, for this label we have 11, for this we have 15, and infinite 19. So to check if this is correct or not, I will have to next dot asm. So if this 0, this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So output first should contain 11. Yeah, it does contain 11. 11, 12, 13, 14. Output D 14. Wait, 14. This is 11, 12, 13, 14. Wait. I'm not reading it correctly, I guess. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, I get it. Okay, let's see what's the problem. Should I even skip this line number? So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if I'm ignoring this instruction, oh yeah, I should be not incrementing it by 2 over here. It should be incremented by 1 only. So let's see, 0, 1, 2, 3, and 4. Yeah, now it is correct. So we have 10, 13, 16. 0, 1, 2, 3 4 5 6 7 8 9, and this is 10, so we have 10 11 12 13, this is 13 14 15 and 16. Awesome. So we have this values. Now we have completed the first pass logic. What do I need to do now? I need to implement the logic for second pass. Second pass. Where should I implement it? I think we should get this first pass out of this symbol table, and it should have its own class. Will it work? So if I create a pass class and let's see if it contains a post pass method and also a second pass method. During second pass method also we are going to run through entire program, so I think we should do that. We should have a class called, well, I can't use pass as the name because it is a keyword for it is a keyword in Python. So what should I call it? Pass with 3s. That will work. Init function. What should we initialize over here? Do we need to initialize anything? Yeah, we do. So for this pass function, instead of opening this files over here, we can open it in this class. So how can we do it? We'll call the pass object. Well, no, let's keep the logic here only, but I can pass the program over here. And I can initialize the program. Now we'll have program inside this class. We don't need this. and I can replace this. Org with self dot prog just add one. Okay, now let's see what we need to do. So now instead of calling this function directly, I need to create object of pass. So pass, let's call it pass the ASM. Okay, after that I call pass.first pass, and this time I don't need to pass the program. This will execute the first. Let's see, let's check if this still works or not. There's no attribute, of course. Yes. Now we need to change this as well. Instead of calling self exist, so I should pass the symbolic table as well. Sim tab, yeah, I'll call it sim tab self dot sim tab is equal to sim tab. I'm sure I'm not doing it the right way, but just going to run with it. So now instead of calling self.exist, I should call sim tab exist. Sim tab add symbol. Let's see if this works or not now. Okay, wait. What did I do? Yeah, I didn't pass the sim tab. Sim tab is not defined. Cause it is not defined. Awesome, so we are getting the output now. Now what else do we need to do? Yeah, so we are trying to implement the second pass, sec pass. So what do we need to do inside sec pass? First we need a variable n, and it should be set to 16 initial. Let me copy it. So first we'll self.pro. Okay. Wait, but I think we have a problem. So suppose if I call, so what if I call the second pass after first pass? What happens then? I don't think it will work. This might not work, so sec. I'm sure this is not going to work. Yeah, see, so there are no second pass logs because during the first pass only we have exhausted this instruction, all the instruction from the self.proc. So we have to start, we have read all the content of the file, so we have to start reading it again. So how can we do that? Do we have to open it again? Yeah, so I think we have to open it again. So instead of opening the file over here, we will have to open it, the passes. So now instead of doing this, okay, so now we don't need to pass this probe variable. Let's get rid of this. What happened? Prog is not defined. Where are we using prog? Yeah, I need to delete this. Awesome. So this time we are getting the second logs. So cool. So our second pass method is working. What do we need to do inside second pass? Okay, first we're getting a variable, assigning 16 to it. Now we need to pass the instruction. Now after passing the instruction, we have to check if the instruction is at symbol. If first we have to check if the instruction is of type. Wait, so now there's a problem. Yeah, I think so. Now before we were not having at symbol, so I wrote this function method value. That means we only had constant values with at symbols, so I was directly storing it as value. But this time we don't have constant value, we have a symbol, and this symbol is either a variable or a label, like this one, at loop or at sum. We just need to check if this symbol exists, so we already have that function if exist. So what do we need to do now? I need to call if self dot sim tab, and I will have to pass the symbol. So now in this case, to get the symbol, let's copy this. Now we can't get 1 to -1, but what we should do instead is okay. But first, before that, we have to check if it is of type A or not. So to write a condition if p dot type equal to A. In this case, I will get the symbol, and it will be from 1 to, and in this case I won't be passing -1, so this will give the whole symbol up to the end. Now I can call sim dot exist, and I should pass the symbol. Symbol exists, that means the value is inside the table. So in that case, what we need to do is use the value to complete the instruction translation. So that means I need to do all of this thing. I have to get the code. So let me copy this. But I also have to open up this file for writing. So yeah, this time also I will open up over here. Okay, and instead of calling it compare, I should be calling it hack. So now if the symbol exists, then I need to get the code value. So what should I pass? Okay, so I need to create a method to get the values as well. Def get val symbol. I just need to return self dot symbols dot get symbol. So this will return the value. Now I can call self dot sim tab get val of this symbol. This will return us the value and we'll get the code of that value, and I need to write it inside the hex file. So I guess this will give us the value for A type. Now if the symbol is not found, in that case what we need to do, add the symbol to the symbolic table, use and to complete the answer. Yeah, so in this case I need to add the symbol. So add sim tab that add, what is it, add sim. I'll pass the symbol and the value will be n. In this case as well I will c dot just pass n. And after that I also need to increment this, and this is just for instruction type A. Now what if we have p dot type equal to C? In this case, well, in this case we don't need to take care of all this symbolic shit. We can just translate the instruction directly. So for that we have this code. I will first call code with p dot destination. What will this return? If it is of type C, DCJ, and instead of writing it to compare, I will have to write it to hack. I think this is it. This will take care of everything. So let me copy or cut this, and yeah, I will pass it over here. So let's check if this works or not. Okay, we have an indentation error. Where do we have an error? Yeah, I know why. Let's see, do we have the output or not? Max. Yeah, we do have max.l. But is it the correct output? So to check if this is correct, I will have to open up the simulator. So to Tetris tools, what should I open? Okay, assembler. So first I will open up let's see, max. And max hack. This is our own translated file, so let me run it. This will give us the translation using this assembler, and it will compare it with our output. Okay, we have a failure at this line. Why? Okay, yeah, I think why. At output. So this is a symbolic instruction. That means let me unload this file first. And see what it looks like. And I will also check max dot hack. This is our own program. So if we compare, we had problem at this line output, which is this instruction. We have 1101. Not 1101, 1101. Here we have 1100. So it seems that at output, this value of output t is incorrect. But for output first, we have the correct value. What's the value? The value is 1010. So this is 1 2 4 8. So 10 0 1 2 3 4 5 6 7 8 9 and 10. So output first is 10, 11 and 12. So output t should be 12. It was 12, right? 10, 11 and 12. But what do we have here? 1, is this 12? 1 2 4 and 8. Yeah, it is 12, but we have 13. Why do we have 13? Okay, let's see. So during the second pass, during the first pass, if it is of type L, we are incrementing the line number. So what will happen in this case is, when we come to this instruction, line number will become 10 and we are storing 10 for output first, and for the next instruction this will be, line number will become 11 for, okay, I see what issue we have. So instead of incrementing this line number, line plus plus, what if I do this? Wait, do we not have this operator in Python? Okay, since we don't have the increment operator, okay, I will just use the normal operator then. Okay, let's check mess. What happened? Yeah, max dot at. So now we do have 12, so this will work now. Let me load maxsec.l this time, and let's let it run. Okay, so this time the comparison ended successfully. That means our program is working. but let's test this assembler for some more programs, which I tested it for Max. Okay, now let's test it for the rectangle. Rect Okay, let's load this program rect and the comparison file. We have failure at the first line. What happened at 0? Why do we have 1? What happened? So let's see, let's walk through it. We are assigning the predefined symbol, and after that we are doing the first pass. First pass will ignore this instruction at A. Okay, and during the second pass, what happens? We are opening the file for writing, opening the file for reading, and after that and 16. So if the instruction is of type A, we get the symbol and check if symbol exists. In this case, it should return false because this is not a symbol, it's a... Okay, I see. This is a value, not a symbol. Okay, so now we have a problem. So what is happening is, first it will go inside this condition because this is of type A, and extract this 0 inside the symbol and check if it exists inside the symbol table or not. If it doesn't exist, then it will add this symbol and n will be 16. So this is not a variable, it's a constant value. So we'll have to check if it is a variable or a constant value. But how will we distinguish it? Because both the variables and the constant values will be of type string. Both are characters. So how will we distinguish if it is a constant value or not? Python check if string is decimal constant or not. This is integer. We have this method is integer. Also we have is instance. New window file. What does it mean? So I can use a try catch, try except. Yeah, let's use try except, because we do need a condition anyway. So I will do try. Except value error. Val is equal to int symbol. So if it is an integer, we will have the value inside val. So what do we need to do? If it is not a symbol, that means it will go into this error loop. In this case, we need to execute this commands. This will add the symbol and the n and do n+1. But if it is not, value is equal to int, and what do we need to do? We still need to write it, right? So now I can pass this here. Well, so this might work. So let's load it now. So this time we are not getting that word inside the strings. Let's compare it again now. All right, so the comparison ended successfully. So see, that's why we have to check for different programs. During this max program, we couldn't catch this bug, but during the translation of rectangle program, we did come across that bug. And now we also have the Pong, but it is going to take a hell lot of time to compare it. Let's first translate it Pong as some. Oh, wait. What is this? I guess all of them are the labels. So, and now we can't check the compare file using this program because it will take a hell lot of time. Let's see if there is another way. We do have the hack. Yeah, this is the translated program. Now we need to copy it, compare it with this. So is there a faster way to compare? Let's see. Suppose we translate the program using the supplied assembler producing a binary file. Load it into the supplied visual assembler as a source program and let me try to load the program anyway. The Pong. This time I'm not going to load the comparison. Oh damn, it's going to take a hell lot of time to compare, translate it. Is there not a better way? Fast translation. Yeah, we do need fast translation. Awesome. So we do have the fast translation, and this time I can load the comparison file and do fast translation. Awesome. The comparison ended successfully as well, and this was fast. That means our assembler is bug free, at least for this programs that we are given. For max, add, and pong and rect, our assembler is translating it correctly. So I think this is it for the assembler. Let's see if we can improve this. Before we do that, let me remove these lines. Let me also remove this lines of code. We have gotten rid of all the log statement. Okay. So let me remove this file. Okay, so this time we don't have pong hack. So let's try to compile it now. So now we do have this, and let's load this again. Awesome, it is working. What else can we do to optimize this code? Getting the symbol table, pass, first pass, second pass. I don't think we need to do anything else with this code. Maybe we'll come back to it again in the future and try to optimize it. But as per my limited knowledge of Python, I can't think of anything else to do with this code. So I will leave it as it is. And so yeah, with this we have completed all the projects of the part 1 of Nand2Tetris calls. Part 1, inside part 1, let's review what we did. We created this Boolean logic gates, Boolean arithmetic, sequential logic, machine language. We wrote the assembly programs, then we created the computer architecture, basically assembled the CPU and the whole computer, and we wrote an assembler. So that was it for the part 1. We had 6 projects and we completed all of them successfully. So now part 2 contains all of these projects where we write, what do we write? We write a higher language, I guess, and we also write a whole operating system. So I don't know when I will be doing this part 2. I think I will start it immediately, and after I have done this week 7 of part 2, I will come back to this project 7. And maybe, I don't think I will be streaming later today, or maybe I will. Let's see what we will do. But this is it for this stream, I guess. Alright then, bye. I will see you guys in the next stream. Bye.